So now we're going to look at the case of a hanging weight hanging from a string, or a plumb bob. And so this is the Earth here, and this just looks like the example we were talking about a minute ago. I've intentionally drawn the Earth oblate. It looks like a squashed sphere, and I did that because that's how the Earth actually looks. And so if I have something hanging from a string, which we're going to pretend we do, the T is along the direction of the string, but the tension actually doesn't point directly opposite the gravitational force from the Earth because of this rotational motion. There's effectively an outward force that causes the plumb bob to swing, to hang not straight down towards the center, but slightly outward from that. And so we have three forces acting on the plumb bob. The centrifugal force, right, from the fact that the coordinate system is circling around the rotational axis of the Earth, like that, at angular velocity omega, right? And then there's a tension and mg0, and so g0 is the magnitude and direction of the acceleration of gravity. It's given to g0 because often we will just look at mg as being opposite the direction of tension, but technically that's just the sum of these two vectors. And so we're often just treating these two guys together as mg. And so this is the guy that points right at the center of the Earth. T is the tension in the string. Again, we've got the three forces in this sort of free body diagram without the coordinate system and stuff like that. And again, minus ma0 is the force due to the fact that the frame is accelerating. We called this the centrifugal force of the frame. And then so the tension is not in line with g0. It's not opposite g0 because of this minus ma, because the frame is rotating. It would be opposite if you were on Venus and your planet, or on a planet that wasn't rotating, right? The moon is barely rotating. The moon is rotating once a month, so they would be pretty close to opposite each other on a non-rotating planet. And so what we want to be able to do is redraw these vectors this way. We want to say, look, here's my tension, and here's my mg0. So this is tension. This is this is mg0, and this is minus ma0, and that is the deflection angle, which we call epsilon. And so on the next sheet, we're going to use the law of sines to figure out what that is. So this is a redraw of those forces from a second ago, and I'm just going to redraw them as a triangle. And so I'm going to say, I know I'm not doing a very good job of this. Whoops. Let me try that again. The scale in my drawing isn't very good. So this is going to be my mg0. This is going to be my minus ma0, and this is going to be my tension, right? This is the angle I'm interested in, and I call that epsilon. But this angle here is the thing we called lambda from the previous drawing. This is the latitude angle. This is the point on the Earth where the event is happening, say, and this is the center of the Earth, and that's the pointing towards the equator, and so so that's the latitude angle. And so we can use the law of sines which you can look up or you can remember. It's the sine of an angle divided by its opposite side is the equal for all angles. And so I can say, I can just come over here and say the sine of epsilon, the thing I want, over ma0, I'm just going to use the magnitude of it, is equal to the sine of lambda divided by the tension. And so Normally, way back in basic physics, general physics 1, we said, look, if an object is just hanging straight down, the tension is just the same as mg, right? Mg pulls up, and tension pulls up, and mg pulls down, and so those two things are equal. And so we would write this way. We would say sine of epsilon over ma0 is equal to sine of lambda over mg, right? But we already said ma0 is just equal to m omega squared radius of the earth cosine lambda, right? We figured this out earlier. And so we can say sine of epsilon is equal to, we know the angle is going to be very small, approximately epsilon, which is can I slide that up just a little bit? So it's equal to epsilon in radians is equal to omega squared, where that's the rotational velocity of the Earth, the angular velocity of the Earth by its rotation. Re is the radius of the Earth. Lambda is the latitude, depending on what latitude you pick, over 2g. The magnitude of g doesn't differ significantly from the magnitude of g naught, and so if I calculate this thing, I get about 1.7 times 10 to the minus 3 radians, or about 0.1 degrees, something like that.